one of the problems, it was like a line that went over the parabola for most of the way, but then it said that the parabola was the upper function for some reason. It's kind of confusing.
Really?
So how do you check which one's the upper function again?
It doesn't matter. And here's why. What you want to make sure that you get are points of intersection, right? So you've got to make sure you get every single point of intersection and work your way from left to right from one intersection point to the next. And Jake, you can do it in any order that you like, as long as you're mechanically sound when you plug stuff in an anti-derive. If you get a negative, just absolutely value it. But it's got to be from one intersection point to the next, right? You can't skip that. But maybe just read it wrong or maybe whatever. But it doesn't really make any difference. Just don't drop a point of intersection. Awesome. All right, guys. So here's what we're doing today. I'm going to record class. So we're going to move into three-dimensional shapes. Okay, so this is 6.2. This is volumes of solids of revolution. Volumes of solids of revolution. And you'll see why they name it this, why they call it that right now. So basically what we're going to be doing is they're going to be giving you a two-dimensional region, just like they did in 6.1, right? It's going to be bounded by two or more curves. And they're going to take that and they're going to revolve it around an axis of revolution, thereby creating a three-dimensional shape, okay? And you can already, like, imagine it's got, like, manufacturing implications, right? Design, things like that. Business applications, obviously, when you're talking about raw materials and making, like, tons of, like, whatever, titanium jet parts or whatever. So if you got something like this, start off with some pretty easy curves. And by the way, the graphing will not be difficult, I promise you. I'll either give you the picture or I'll tell you what it is. So you don't have to worry about graphing by hand. But if you've got like y is equal to x squared, let's do x is equal to 2 and y is equal to 0. I'm talking about this like semi-triangular-ish shape right here, right? And then I'm going to tell you the axis of revolution for each individual problem, basically. So let's just start out by just revolving it around the x-axis, right? So you can kind of imagine that if you had like this like shape cut out of a piece of paper, this is like a little stick or whatever, and you taped it to it, and you started spinning it around, it would trace out this like triangular-ish, like a thumbtack, basically, pointing this direction, right? So if I spin this around the x-axis, you're going to get something that looks like this. Try to draw this three-dimensionally. You're going to get something that kind of looks. It's going to be bigger. Let me try this again. If you look at that like three-dimensionally, right? So you can actually see the base of that shape. So this just goes around here. And what you're going to be tasked with today then is coming up with the volume of that shape. Here's how we're going to do it. Right? We're going to do it just like we did it with area. We're going to start off with a representative rectangle. And the rectangle, in this case, is going to be perpendicular to the axis of revolution. Because here's what I want to do. I just take this thing right here. And I spin this around the x-axis like that. Do you guys agree that you're going to get this like disc shape? So I'm going to make like the rectangle, whatever, half a unit wide or a quarter of a unit wide, right? And then what I'm going to do is I'll just move over and make the next one. If I move to the right, it'll just be have a little larger radius, basically, right? And I'm going to move all the way from 0 all the way over to 2 in this case. So I'm going to like estimate this shape. If I look at this shape in profile, you guys agree it's going to look something like that. And if I use like wide rectangles and spin them around and use that to estimate my volume, do you guys agree I'm just going to get like a stack of discs, basically, or coins, basically, moving from right to left. So I'll get something that looks kind of like this. Just exaggerate the width here a little bit. Are you guys with me? Obviously, this volume of this stack of coins is going to be either more or less than this curve right here, than this shape here. The idea then is to use the magic of calculus, the magic of integration, to force these disks to become infinitely thin, and then you get less and less of a pixelated shape, and you get more and more of a smooth shape, right? Especially when you drive these to be infinitely thin. So that's where we're going. It's kind of cool. That integral then, the answer to that integral will be the actual volume of that shape, of this shape, the smooth shape, right? Because the estimate will be so close that it will no longer be an estimate, just like we did with area. Same concept. How we doing, people? We good? Excellent. So how about this? Let's just look at this then, just the volume of this disk. And I'll just put the disk kind of on its side, get kind of a better idea of that equation. Anyone know what the equation for the volume of a cylinder is? Because that's essentially what that is, right? I mean, coins are just like really short cylinders, basically. Juliana, do you remember?
What if like pi r times height?
Beautiful. Pi r, actually squared, right? Because it's area of the base times how tall it is. So I'll just call that h. And that's what I want to build into my integral, right? So check this out. Hey, James, come on in. No. Mary, thank you. Okay, so here's what we're gonna do. I'm gonna build this into the integral. Pi is just a constant. I'll just put that up front, right? Now, here's the deal. What if I take this and I put it this direction? Do you guys agree the concept or the idea behind this is to make this infinitely thin? So if I have an infinitely thin movement along the x-axis, or not movement, measurement along the x-axis, we had a calculus term for that. What do we call that? What's that?
dx.
Beautiful. Dx. Do you guys agree? Dx is a teeny, teeny little measurement along the x. Beautiful, Jake. So this h is going to be dx. How are we doing, guys? We all good? Now all you got to do is get the radius. The radius in this case goes from here up to there. What is that measurement? Yes, Victoria.
X squared.
Beautiful. It is the function, right? Depending on what curve we're using. In this case, it is going to be x squared. So in this case, right, this will be x squared. I want to square that. And now all I got to do is integrate from where to where, Tim?
0 to 2.
Love it. 0 to 2. Now, the way we're going to work this is, right? First of all, I want to think about whether it's a dx or dy problem. The height of the rectangles, the width of the rectangles are along the x-axis. That's what makes this a dx problem. The next thing is I'm going to fill this in. So I want to go low x to high x. And then really all you got to get is the radius expression. In this case, it is the curve because you're going from the x-axis up to the curve. Beautiful, Victoria. How are we doing, people? So then look, all you got to do is just solve this, right? Isn't this pi times the integral from 0 to 2 of x to the 4th dx? Anti-derive this, plug in 2, plug in 0, and subtract them. I got pi times 1/5 x to the 5th going from 0 to 2. Make sure these guys can see this. My answer then is going to be 32 pi over 5 minus 0. 32 pi over 5 is actually the volume in whatever unit we're measuring, right? Millimeters, centimeters, that'll be cubic units. What you think? It's not too bad. It's actually kind of cool the way this works. Chase, I know you came in late. Are you kind of feeling okay with this?
I think so.
Okay. We're moving from like a pixelated stack of coins to estimate the volume of that shape to ones that have infinitely thin coins, give you a non-pixelated, super smooth estimate of the actual volume.
So the height is the radius squared?
You bet. Now listen, I will tell you this. What Chase is asking is really important because getting the expression for the radius is the hardest part of this entire process. So I'm going to put a drawing in your notes that I'm going to refer back to throughout this chapter. Okay, we're going to use this over and over and over again. I don't want to insult anyone's intelligence. When you first see it, you're like, duh. But I'm telling you, it's easy to forget and to get it all mixed up in your brain. So let's put that in your notes now, and then I'll work a few more of these problems. We'll be good. All right. Before I do that, any questions? Feeling okay, Grayson? Good to go? Okay, cool. Okay, so here's the picture that's super important that we're going to use over and over and over again. I just got some curve, whatever. We'll just call this f of x. Actually, I'm going to erase it. It doesn't even really matter what we call it. I pick some point at random on this curve. Do you guys agree that the distance from here to here is just y? That's not saying, right? You learned that in third grade. This from here to here is x. And you'll notice, right? Y is from the x-axis up. X is from the y-axis over, right? Okay, now there's one other rule I'm going to refer back to a lot as we go through this process, and it is this. You must use subtraction to find the length of any segment which is not measured from an axis. You must use subtraction to find the length of any segment which is not measured from an axis, either the x-axis or the y-axis. So let me show you what I mean. Like for instance, let's say this is f of x, right? And over here, this line is like x equals 7. We're assuming this is to the left of 7, right? Then if this is x, what is this? Go for it, Gracie. You got it. And that's what I mean by using subtraction, right? You've got to back into that measurement. I start with what I know, I take away the variable version of it, and I get the what is left over. So from here to here, 7 minus x. Again, it's not difficult. I just want to make sure that you see it. Let's call this y is equal to 8. I got to use subtraction to measure this because I am not measuring from the x-axis. You guys agree? So this measurement is going to be 8 take away y. Are we good to go? Use the same curves here just for a second to speed things along a little bit. This is y is equal to x squared. This is x is equal to 2. Y is equal to 0. And please, guys, slow me down if you feel like you're falling behind or if you're just not seeing what we're doing here. Now I want to go around or about, rather, x equals 2. Can you see that you get roughly the same shape, just now pointing upward, right? So it's going to look something, like this. Now, remember what we want, guys. We want stacks of coins, right, that we're driving to be infinitely thin, which means now the coins have to be lying horizontally, basically, right? Which means in order to create the coin or the disc, I've got to have my representative rectangle going this direction. And then when I spin that around here, I'm going to get that. So that coin in the stack will be that big. Wider as it gets lower, right, Jake? And then it gets really, really thin or So now check this out. If it's, remember, you're always focused in on the thin side, right? Because I'm going to make these infinitely thin. This is going to be a dy problem. Do you guys agree? And again, that's the height of the cylinder, right? So the height of the cylinder is this measurement right here. It's a tiny measurement along the y-axis. This is a dy problem. So again, that's what I'm going to always start this process by writing down whether it's a dx or a dy problem. That is important because it will indirectly give me these bounds here. Connor, what do you think these bounds might be?
0 to 4.
Beautiful. Low y to the high y. And isn't this highest y, this point right here is the point 2, 4. This is 2, 0. The lowest y being 0, highest y being 4. You doing okay, Jake? You good? Awesome, awesome. Pretty good? Sweet. We got pi out front. Hey, partial credit. Perfect. By the way, pi's a constant, right? So I just move it out of the way, get it out of the way. Cool. Now you got to get the radius. So this goes, in this case, the axis of revolution over to there. Do I need subtraction to find that? I do. How do you know, Tim?
Because it's on an axis.
Yeah, you're not measuring from an x or y axis. I mean, obviously, this is an axis of revolution. That doesn't count, right? Okay, now, here we go. How am I going to find this? What is this? Well, let me back up. What is this? 2. What is this? Just from here to here. Beautiful. Do you guys agree it's x? Listen, anytime you go from the y-axis over, it's just x. So what is this? 2 minus x. It's 2, take away that x, and you're left with what's between your fingers. Listen, they're basically 2 different x values. Do you guys agree? It's like x1 minus x2. It's just that x1 is constant, so I just make it 2. How you doing, Jackie? You okay?
Yeah.
Okay, beautiful. So this is going to be 2 minus x quantity squared. What's the problem with that?
Oh my god, X's and Y.
I got x's and y's. This is no good. Chase, any ideas how to get rid of the x and get a y?
We could. No.
Anyone have an idea?
Well, y equals x squared.
Oh. So what's x?
Root 1 squared.
Square root of y. Ain't it? By the way, I only want the positive, right? So I don't need to worry about plus or minus. So don't worry about that. I just need square root of y. So I'm going to take this out. This is then pi going from 0 to 4. This is 2 minus square root of y, quantity squared, dy. By the way, guys, tonight, the hardest part for sure is setting these up. Because every single one of these are pretty easy to integrate. Like, how would you integrate this, Colin?
So use u equals, so just kind of, I would just multiply it through.
Yeah, you would FOIL it out, right? FOIL them out, do them all separately. You guys agree? And none of that's hard. It's not like you don't even need to use substitution. Although I suppose you could use your substitution, but you don't need it. You could FOIL that out and do them all separately. Plug in 4, plug in 0, subtract them in that order, multiply the final answer by pi, right? You guys, no one's spacing out. We're all good, right? So I'm going to leave this up to you. The integration part will be up to you. You just want to set these up tonight? Go for it. I may have you work through a few on the quiz, but it won't be challenging, right? I'd rather ask you more setup problems than have you actually go through it. We're going back to integration in chapter 7. I'll get you there. So, yes, sir.
So I noticed you only run into the problem where you have a y and an x if you're rotating it around the point, or like the rotation of axis is vertical. You only run into the problem of having an x and a y versus on the first one you did, if you rotated it horizontal, you didn't have that problem.
Well, you can run into it just about any time. I mean, you will have conflicts from time to time between x's and y's, but you just use the technique that we just did. In the end, though, I need an integrand with all agreed variables, right? Yeah. I hope I'm answering your question, Jake. I don't mean to be evasive, but yeah, it's the same technique no matter how you get there. Okay, how we doing, people? So setup only, if I said it, that would be this right here. I'm good? Great, all right, let's continue. This y equals x squared. Let's do y is equal to 4. Let's go around here. Oh, and x equals 1. I don't know if you can visualize this. You guys agree you're gonna get something that looks ish like that, more or less, kind of like that, maybe a sharper. This isn't big enough, but if I take this around here, I'm gonna get something that looks like that, yeah, okay. Do I have vertical or horizontal representative rectangles? Beautiful, gonna be vertical. Do you guys agree? That's the only way you're gonna get like coins or discs. It's gotta be perpendicular to the axis of revolution. So I'm just gonna draw this in, and that one coin there, right, will be like, whatever, it's gonna be that big. It's the worst drawing ever, but you get the idea. Okay, hey Grace, dx or dy problem? Dx, beautiful. So I got pi, dx, partial credit. Hey Brenna, integrating from where to where? You're close. I think it's just 2, right? Yeah. Because isn't this point here going to be 2, 4? So it's low x to high x. By the way, also the reason that you would start here, right? So that kind of clues you in as to where you're looking. So you're only looking at the x values once you've established that it is a dx problem. All right, cool. Hey, do I need subtraction for this, Bella?
Yeah.
Yep, you do. What is this measurement?
Where?
What's this? Just
Y.
that from there to there. Beautiful. So this distance right here, Bella, is?
4 minus y.
Howdy. Can't have y in there. Lindsay, what is y?
X squared.
Love it. End of story. Kind of cool. Grayson.
Are we gonna get to a point where we have to do these on axis of rotation that's not horizontal?
No. Topic for another class. There is a way to do it, but we're not doing it. Okay, now, I like your enthusiasm with Grayson.
I was not.
You would just get up and walk out. Like, nope, not doing it. I'll take the 0. Thanks. All right, here we go. Ready? 5 minutes. Great time for a snowstorm. All right, so let's do same curves. But now let's go around here. Yep. Okay, now hang on here. Do you guys see that it looks, it's like a vase shape or a vase? Something like that? A little bit? You see that?
Yeah.
Okay, cool. Here's how we're gonna do this. What I'm gonna do is this. I'm gonna start off with a solid cylinder. What I'm gonna do then is I'm going to take out the part I don't want. Which gives me this. How's that for a symbol equation? Start with this, take out the innards, you're left with this. Let me say this again. Start with this, take this out, you're left with this. So everyone see what's going on here. From a disk perspective, do you guys agree? You're going to start with the solid disk. You're going to subtract out the inner disk. And you're going to get right the world's worst donut. It's actually called a washer, right?
That almost makes sense.
This is called a washer method because that looks like a washer, right? All right, cool. So you start with the outer, you take away the inner, you end up with a washer. Same theory, it's just two separate disk methods, one subtracted from the other. Exactly the same thing, okay? All right, so let's do it with this picture here. Can I erase this thing here? Everyone knows where we're going, right? Going toward this picture. Yeah. All right, cool. So now, here's the deal. The minute I figure out that this is a washer method, I'd like you to do this. I want you to split it into two separate integrals. I will tell you this. When you look up the answers in the back of the book, they combine it into a single integral. I don't like that. It starts to look too much like using subtraction to find the radius. I don't like it. So I'm going to split it out. If you want to do it on the test and quiz, I'll figure it out. But just know that when you look at the answers, these will be combined, okay? Is this going to be a dx or dy problem? Got to be dy. Here's why. It has to be perpendicular to the axis of revolution. Otherwise, you're not going to get disks, right? Your rectangle has to go around here to create a disk, to create this disk right here. Does everybody see that? Okay, good. So these are both dy problems. I'm going to integrate, Jackie, from where to where?
We're gonna integrate from 0 to 4.
Beautiful. Low y to high y. You guys are doing great, I think.
Why do you do the integration method for like the outside cylinder?
Say it one more time.
Like,
You
why-
don't. You don't.
So you can't. So
You don't.
You can just do like.
You guys know what Colin's saying? He's like, this is not a calculus problem. This is pi squared times height. Why do we do calculus? Because we're in calculus and we can do it with calculus. So we're gonna, but you don't need to. You guys agree? Just pi squared times height. I already know the height is 4, right? I also know the radius is 2. But who cares? It's so much cooler this way. All right, here we go. Ready? What is the radius of those outer? What is this radius right here? It's x, but it's constant, so I can use a constant, right? It's just 2, right? And by the way, if I were to integrate this, plug in 4 and 0, I'd be good here, wouldn't I? I'd get the same thing. You can take my word for it, you will. The bell's going to ring soon. I got to keep going. All right, now we got to take out the innards. Isn't it true that the innard goes from the axis of revolution to the closer side? So this just goes from here to the closer side of the shaded area. From here to here. Is everyone seeing this? Cool. What is this measurement?
That's just that.
Excellent. It's a dy problem. Can't have x's in there. What is it?
Oh, I swear this one.
Yeah, the whole thing is y. That's perfect. But I could do this, couldn't I? Yeah, usually the same thing. Tim, I only want to write it that way just because it's consistent, right? With the way we do it, everything else. You are absolutely right. What do you think, people? Yeah, Victoria.
I'm confused on why it's just x instead of x squared.
I'm telling you, I'm going to use this a lot,
We're going
right?
the other way. I thought,
Yeah.
yeah.
If it goes from the y-axis over, it's x every single time. Even, I think, Bella, I think it was you that said, hey, that's x. Yeah, it is x. But it's constant, so you can use 2. Go ahead, Tracy.
What is this gonna be called, like on quizzes and tests, they get the book?
Find the volume of the solid that results when you revolve around an axis. It'll be really clear. Yeah.
So you have to use the washer method for that because you couldn't make discs either way because neither.
Yeah, represent the volume that you are looking for. This inner disk is waste volume. I don't want this. This outer includes stuff I don't want. The only way to get there is with subtraction. Start with more than you want, take away what you don't want, you're left with what you do want. We should have t-shirts that say that because it's true throughout life. Yes, go ahead, Tim.
Don't you kind of do that with all of them, because if it's not like a bowl, then you're just cutting away the part that is a bowl.
That makes sense.
It's like David, like you just chip off all the parts that don't look like David.
Yeah. So you're
Okay,
kinda-
here's what I want you guys to work on for tomorrow. Well, like the first two that we did, or first three that we did, I wanted to keep it all, so I took away nothing. I think that's what you're asking. I don't know. Page 428. 1 through 11 odd. Now, guys, on these, again, you can just set these up if you like, all right? And then I'm going to give you some true false to look at. Page 418, 79 to 81. Any other questions before we get out of here, guys? Because I think there's no bells, so have a great day. Excuse me, there are bells, so see ya. Thank you.
Still 5 minute passing periods, right?
It's 4-minute passing periods.
Oh.
They had a chance to plow the halls, Colin. That's why you can walk more quickly.